Now what we're going to talk about in this video is we're going to talk about a couple of the applications that we can use integration for. Now a couple of them build on some of the higher material that we looked at previously, and what we're going to do is talk over the theory behind that, look at how we can apply it to a slightly different scenario, and then build this up to calculating the volume of a 3D revolution about the x and the y-axis, taking the shape roughly of a cone or a cylinder. Because these are the kind of applications we want to be able to use this integration for in order to be successful at this level. So let's go back to integration as we covered it at higher, particularly calculating the area between the curve and the x-axis between 2 points. So let's imagine what we're going to do is look at a curve and we want to calculate the area between these points A and B. Let's break this down simply. If you imagine I've re-sketched this, so there's my curve, and let's take O as the origin, and this line here is A, and this line here is B. And let's imagine we take this as a composite shape, because if we want the area here, what we have to do is imagine that we know the area between 0 and A, area then between 0 and B, and subtract them from each other. So essentially what we want is the area of B take away the area of A. That's the basic premise of the whole thing. Now let's imagine what we're going to do is call the distance from 0 to A, we're going to call that x, and we're going to call the distance between A and B h. So what that means is the difference between A and B, i.e. the length of the area that we are looking to calculate. Now what that allows me to define is 4 points. So that allows me to, if I go back to this diagram here, define the points here, 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 and here on my diagram. So let's call those points P, Q, R, and S. Now for those 4 points, we know that they can be approximated as the vertices of some sort of shape. Well, if you look at that, imagine we straighten that line out there. That could roughly be approximated using a trapezium. So what we're able to do is use these vertices in order to be able to calculate the area of this trapezium. Now, going by what we said originally, our point P would P x, 0. Our point Q would be given by x plus h, 0, because it's still on the x-axis. My point R would be given by x plus h, and then the function, so we've called that f of x plus h for the y-coordinate, and my s-coordinate would be given by x, comma, f of x. So that will give me the coordinates and the points of all 4 of my vertices. Now what we're then able to do is use the formula for the area of a trapezium in order to calculate what would roughly be the area of this one. So what that then allows me to say is that my area would be the equivalent of h over 2 bracket f of x plus h plus f of x. So that there would be this rough area here. Now, of course it's going to have an error. We can't just say this is a trapezium because this curve here is not a straight line, so there is going to be some sort of an error that comes into play when we do the calculation. However, in order to calculate that area and make it more and more accurate, what we can do is divide this up and make it smaller and smaller and smaller. So we can let the h, which is the length here between the 2 points, get smaller and smaller and smaller. So now what we've done is we've taken our trapezium and we know that we can then represent this as the A at B. Well, I know this is x plus h. Take away the A, what the A was, which we're going to call x. We can say that that's approximated by h over 2 bracket f of x plus h plus f of x. So what that then means is that we can take our formula for the derivative, which we know is d by dx, is given by the limit as h tends towards 0 of a of x plus h, take away a of x, all over h, And we know that that's then going to equal this all over h as h tends towards 0. So we know that that's then going to be the limit as h tends towards 0 of a half bracket f of x plus h plus f of x. So what that now means is that if I then take the derivative of all of this, or notate it using the derivative, I've got a dashed of x, that equals the limit then, as h tends towards 0, of a half f of x plus h plus f of x. Now previously, we couldn't let h tend towards 0 because we were dividing by it in this expression here. However, there's no division by h here, so what I can say is then, as h tends towards 0, that equals a half of f of x plus f of x. So I know then that a dashed of x is equal to f of x. What that then means is that since a dashed of x equals f of x, if I integrate it to reverse this process, I can then say that a of x, so the area under the curve between these 2 points, is the equivalent of the integral from a to b of f of x dx. So what this does is this proves the concept we discussed at higher, where we approximate the area under the curve using a shape, in this case a trapezium, and then make the width of that trapezium so small that it gets to a point where we're essentially adding up an infinitely amounted number of thin strips that allow us to calculate the area accurately, and we can write it as a of x equals the integral from a to b of f of x dx. Now we can apply the same simple premise to calculating the area between a curve and the y-axis. Now what we have to remember in this process is that we've got y equals f of x for our curve. Now to calculate the area between the curve and the y-axis, so in this case here, what we have to do is change the subject of the formula to x and make x the dependent variable in terms of y. So what I'd have to do is take this and say that I know then that x is equal to f minus 1 of y. So if I give you an f of b here, I can use the fact that x is the inverse function of that to work back the way and get what the b is. Or vice versa, I can use the b to then calculate the limits of my f. Now, we could go through all this process again, but it is the same idea. We can approximate it using a trapezium, use the formula for the area of a trapezium in order to then be able to calculate the area here using an approximate value, but then let it get infinitely smaller so that we get more and more accuracy within it. What we're then able to do is the exact same thing. So let's call this one b of x. So that would be the area here. What we then know is that that's going to be given by the integral between f of a and f of b of the inverse function of y dy. Now it's changed to dy, remember, because we've changed the subject of the formula and the dependence into the y value, not the x. So all we've essentially done is to calculate area between a curve and the y-axis is essentially flipped around the variables to make the dependence go the other direction, and then use that to calculate new limits to get a new formula for the area. Another thing we also have to be able to think about is the volume of revolution on the x-axis. Now, we're going to take the premise that the integral again between a and b is equal to the area of this little section here. Now, what we have to think about doing is we have to think about the fact that what we're going to do is take each of these strips, as we're going to think about it, and revolve it 360 degrees throughout the x-axis. So we're going to revolve it 360 degrees around there. Now what this is going to do is, as we take every strip, so let's imagine I'm going to draw on a strip here, and I revolve it round this axis here, what that's going to actually do is create a cylinder the whole way round. So let's imagine I'm going to draw that for you there. So there is my x-axis going through here. Let's imagine that there's my A, and there's the second point that it's going to be. What I've essentially done, I'm going to take this section here, I'm going to revolve it around the x-axis 360 degrees, so that's the top and the bottom of it, and that then is going to give me a cylinder-esque shape going around my x-axis. And what we know is to get the entire volume that we've calculated and created by revolving this around the x-axis, we're going to have to add up every single one of these. So we're going to have to add up every single one of these little bits here. Now we know the volume of one of these. It's given by the volume of our cylinder, which is pi r squared h. Now if we look at this, we know that r is the distance between the x-axis and the curve. So there's my f of x, which tells you that. So I know in this case that r is going to be f of x. Pi, well, pi is self-explanatory. And h is the distance along here. Now what we're going to do is we're going to denote h as being what's called delta x. Now delta x is going to represent the distance between each of the sections that we're going to define. In ideal scenarios, we want this delta x to be as small as is humanly possible to give us the most accuracy. What we're then able to do is redefine our volume as the volume equals pi times r squared, so times the f of x squared times my h, which is going to be given by this delta x here. Now what I have to do is I'm going to add every single one of these elements here. So I know the entire volume is going to be given by the sum from x equals a to b along the x-axis of pi times this f of x squared delta x. So that there is going to give me the entire volume of revolution that I'm going to create here. Now what we're going to then do is take this and say that what I want to do is calculate the volume, and because I want delta x to be as small as possible, I want that to be the limit as delta x tends towards 0 of the sum from x equals a to b of pi f of x all squared delta x. Now this here is the equivalent formula of an integral. So this here is the same as calculating the integral from a to b of pi times the f of x squared dx. So what that then allows me to say is I can take this and say then that the volume v can be given by a to b, the integral from a to b of pi. Now f of x, remember we denote that most of the time as y, so pi times y squared dx. So that there is the volume of a shape where we calculate the revolution of the curve around the x-axis. So that's the formula we would use for that. We can apply the same sort of concept for when we're looking for the volume of revolution around the y-axis. So let's imagine we've got this shape here, and there's my curve there. So again, let's call that f of x, which we're going to state equal to y. Now I can use the same principle as I had before, where I know from that the x is equal to the inverse function of y, and I know that I've got my two limits here. So this one here is going to be given by f of a, and this one is going to be up here, that's going to be given by my f of b. So again, what I'm going to be doing is changing the subject of the formula slightly. Now the theory remains the same. We want the sum of what essentially will be a lot of cylinders here, but the cylinders to be as small as possible. So that's then going to give me the same style of formula. The only difference going to be is that it's going to be written in terms of y rather than x. So for this sort of equation here, what I want is that the volume equals the integral, this time from f of a to f of b, of pi times f minus 1 of y dy, because of the dependence upon y, which can be written, more often than not, as the integral from f of a to f of b times pi x squared dy. So these scenarios and these formula here, there are a couple of key things that we have to be able to work with, and a couple of key theories we have to remember on how we can apply integration.